Welcome listeners again to our next topic of discussion, that is streams and rivers in the series of lectures on fundamentals of geology. So, in our last lecture, like we have discussed about different processes of weathering, and the first process of erosion that is under the action of gravity, which is referred to as mass wasting. So, the next agent of erosion is obviously your water, which you can find obviously in any stream or river around the globe. So, first obviously we will start with what is a river and how it is contributing to the process of erosion. So, a river is nothing but a natural flowing water course, usually a freshwater stream flowing on the earth's land surface or inside caves towards another water body at a lower elevation, such as an ocean, sea, bay, lake or wetland, or sometimes even another river. Because here I would like to say that many smaller rivers might form a large river in its downslope region. So, rivers play a significant role in shaping the earth's surface. So, water movement between streams and groundwater always takes place, because you can think simply that just above the surface of the earth, whatever water is flowing will be considered under your stream water or river. Whatever water is flowing just beneath the surface of the earth will be treated under groundwater. So, there are two types of water movement between streams and groundwater. The first one is influent or losing reaches loose stream water to the aquifer. That means in case of influent rivers, what is happening that the stream water, whatever is flowing on the surface of the earth, will also get percolated through the surface of the earth into groundwater. So, the groundwater will get recharged again and again. So, whatever water is flowing in the river, it will also contribute significantly to the recharge of the groundwater that is flowing beneath the surface. On the other hand, the other type of river, that is effluent one, it receives water from the aquifer that is present, or the groundwater that is flowing beneath the surface of the earth. So, in case of many, you can say dry regions, when there is no rainfall in the summer period, mainly prior to the arrival of your monsoon, there the main river water is actually drawing water from the groundwater to flow over the surface. On the other hand, when there is ample rainfall, for example, some foreland basin region just beneath a mountain, just you can say in the foreland basin of a mountain, there whatever river is flowing, it can contribute also to the recharge of the groundwater. So, you can see these are the two broad kinds of means river water exchange between in the stream and the groundwater. So, your fresh water is continuously being exchanged between the river water and the groundwater by these two processes or the two kinds of rivers. The first one is influent, when your surface water is recharging the groundwater. It is effluent when it is drawing water from the groundwater. So, stream types according to their annual presence, the first one is your ephemeral streams that flow only during or immediately after periods of rainfall or precipitation. They generally flow less than 30 days per year. Intermittent streams flow only during certain times of the year. Seasonal flow is an intermittent stream, usually lasts longer than 30 days per year. Perennial streams flow continuously during both wet and dry times, and base flow is dependably generated from the movement of the groundwater into the channel. So, you can see there are different types of stream which can become influent sometimes it might also become effluent depending on the type of the stream. There are various parameters or stream parameters for the analysis of a river, that whether you are in the for example in the U stage of a river, you are in the mature stage of a river, you are in the old stage of a river, you can always analyze certain parameters to have an idea on the overall morphology of the river as well as the dynamics, how the river will behave in that particular reach where you are doing your morphometric analysis for a particular basin. So, river basins are taken as units for morphometric analysis, and it is defined as an area of land where surface water enters the area in any direction from any source and converges to a single point before existing the basin. So, here you can see there is a drainage basin, you have a divide which separates both these drainage basins, and these are the several tributaries or lower order streams which are combining to generate a higher order stream. So, we will be coming to that. A river basin's morphometric analysis is carried out under three categories: linear aspect, which are obviously one dimensional, aerial aspect, two dimensional, and relief aspects as well, which are definitely three dimensional, where apart from the length and width of basin, your relief, that is the altitude difference or the elevation change within that basin, is also considered. That is why it is considered under three dimensional analysis or three dimensional morphometric analysis. So, the first linear aspect include the first parameter, that is stream order, which I mentioned that based on the number of smaller order streams that are flowing down a hill slope. For example, this is a river basin. Again, you have these tributaries which are finally joining at certain point, and they are making the main river. So, these tributaries, when they start, they will be considered as your first order. When two first order streams meet, they will be considered as a second order. When finally two second order streams now meet, if it is combining with the first order, a second order is combining with the first order, still it is a second order stream. If two second order streams are combining to generate a new channel, that will be now considered as a third order. So, likewise you can have several orders of stream depending on the presence of different channels, and how many channels are present there, you can make an idea about that. So, this is this was proposed by Stroller's. So, Stroller's method of stream ordering is based on the idea of how your lower order streams are forming your higher order streams. Then you can also think of stream number. The total number of streams in each order is termed as the stream order. So, after stream order, the second step into morphometric analysis is to count the number of stream that are present. Then you have another parameter, that is the bifurcation ratio, and it is the ratio between the number of streams of any given order and the number of streams in the next higher order. So, it can be expressed in the following equation, that your bifurcation ratio is equal to the number of stream by the number of stream plus 1, because you are again considering the next order. So, there has to be an increase in order. So, that is why it is the number of stream or stream number divided by stream number plus 1. Then you have the other linear parameter, that is stream length. It is the total length of all the streams of a particular order, and mean stream length is the average stream length of that order. Then you have also sinusity index. It is the ratio between the actual length of a stream and the length of the expected straight path of the stream. It can be expressed with this following equation, where your sinusity index is equal to the actual length of the stream divided by the expected straight path of the stream. So, based on that, you can have an idea that how sinuous your river is, and based on this parameter also there is, later on we will see, there is a grouping of different types of rivers like braided rivers and your meandering rivers. So, meandering rivers have a very high sinusity index because the expected straight path of the stream is relatively means you can say less in comparison to the actual length of the stream, because of the high sinuous nature of that particular stream. So, that is why the number sinusity index will increase. Then you have the two dimensional aerial aspects or parameters. The first one is your basin shape. The shape of the basins varies from place to place depending upon relief, rock type, slope, geological structures, etc. The ideal shape of a drainage basin resembles a pier. Streams descending from a mountainous zone to hilly or plateau regions generally have more elongated basins compared to those descending from hilly or plateau regions to the plains. Coming into the next one, that is your basin area. that is also a two-dimensional morphometric analysis. So basin area is the area that is drained by the entire river system, or an area drained by a river and its tributaries. So you can see, if you want to find out the basin area, you have to consider all the tributaries and the main river which are also contributing, and these tributaries are contributing to the main river. So then you have the number of total number of streams per unit area, which is also referred to as drainage frequency, that how frequent your occurrence of tributaries or smaller channels in a particular basin area. Then you have the drainage density, is expressed as the ratio of the total length of all the stream channels within a drainage basin to the total area of that basin. So it can be derived as follows, that your drainage density will be equal to the length of all the streams, starting with 1, 2, 3, 4, like this. It will go to the n number. For example, there are 26 streams in a particular basin area. So it will be the length of the first stream plus second, third stream, like that up to the 26th stream, divided by, so the total length you will get divided by total basin area that you already know, simply by demarcating the basin margin. So you can simply find out the drainage density, that how dense your stream network is. And then you have form factor. This is one of the parameters that explain the elongation of a basin. It is defined as the ratio of a basin to its length. So it is the ratio of the basin area to its length of the basin. So from that you can also have an idea about the form factor. So these are extremely useful whenever you are looking at the dynamics of a river in a particular basin. So these individual features will give you an idea about the maturity of that particular river. Then you have the three-dimensional aspect, that is your relief aspect, or your stream slope. So stream slope is nothing but the ratio of the vertical drop of a stream to its horizontal distance. The vertical drop of a stream is determined by subtracting the absolute relief of the stream at its mouth from that of its origin. So you will take the relief or the elevation at the origin of that particular stream to the mouth of that particular stream. Mouth means a small river might drain into, or the mouth of that small river will be a next higher order stream. In case of a very large river, for example Ganga, the mouth will be at the Bay of Bengal. So it is again a matter of your consideration, whether you are considering the complete Ganga alluvial plain and all the basins that are present here, or taking the whole as one basin, or you are analyzing at a different scale individual basins that are constituting the whole Ganga plain. So the horizontal distance of stream is determined by measuring distance between the origin and the mouth of the stream. So if this is the origin of the stream at A, and this is the mouth of that particular stream, that is B, so we will take the horizontal distance as well as we will take the difference in elevation. So your stream gradient or stream slope will be calculated based on the difference in elevation between A and B, and the divided by the horizontal distance between A and B. So obviously you will be able to identify the gradient of that particular slope, the gradient of that particular river. Then you have other parameters like river profile, which is again a three-dimensional you can say morphometric analysis. So your river profile is an outline of the course of the river as seen in a vertical section like this. The profiles of river can be shown in two ways: along the river and also across the river. So along the river you can also see the decrease or fall in the gradient, because obviously it is from upper to the lower course of the river, there will be a change in the slope or change in the gradient of that river. But across the river there will be less change in the gradient. Obviously there will be some changes depending on where you are making that particular section about which you are analyzing in the stream across its length, but usually your gradient will not change when you are doing a profile that is across the stream. Rather it will be extremely distinct when you are taking a profile that is parallel to the stream or along the stream. Then you also can make analysis like hypsometric analysis, and you will get the hypsometric integral, where there is a area height analysis of a river basin, shows the measurement and analysis of relationship between altitude and basin area to understand the degree of dissection and stage of erosion. So, this is also very important when we are talking about the maturity of a river. So, in case of your lower order streams, you can think of, obviously there is changes in the elevation, very distinct changes in elevation. Lower order stream flowing down a mountain, obviously there will be distinct change in the elevation, but the basin area will not be a larger one like we get to see in a river which is, for example, the Ganga river, which is flowing just near our town of or city of Varanasi. So there obviously this hypsometrical integral will have a different value from the value that can be calculated near Gangotri, where the Ganga has originated. So the area height analysis is popularly known as the hypsometric analysis. Hypsometric curves are drawn on graph paper to know the relationship between the area and the height, means the longitudinal profile, that elevation and percentage area to the total river basin. So based on that, you can also have an idea, just by looking at the graph and looking at the value, you can make out that how mature your river is, or you are looking into the which part of a particular river, whether you are in the upper course, you are in the middle course, or you are in the lower course. So based on these graphs, these are extremely useful for the analysis of three-dimensional morphometric analysis. Now, apart from this analysis, what is essential to discuss is the types of fluid flow that can be observed in a stream or in a river. The first one is your lamellar fluid flow that occurs when the fluid flows in parallel layers with no mixing between the layers. There is a quantification called Reynolds number where it is less than 500. Then the other end member, that is the turbulent fluid flow, when there is turbulence in the water. So turbulent flow occurs when the liquid is moving very fast and mixing with different layers, and there is mixing between the layers. So there the Reynolds number is more than 2000. In between this 500 and 2000 value of the Reynolds number, you will get a mixture of laminar and turbulent flow with little mixing. So there will be both lamellar and turbulent flow if the Reynolds number is between 500 to 2000. So now what is again interesting, I discussed this thing a little bit when we discussed the process of erosion in sedimentary rocks, but now we will have a detailed look into this, that broadly again the two end members of any flow is your laminar flow and your turbulent flow. So in case of laminar flow, you can get only one directional flow of the river, like this one is only going in the horizontal direction. But in case of turbulent flow, always apart from this horizontal flow, a vertical flow is, or a vertical component is also coupled with this horizontal one. So you now see that in case of a laminar flow, where there is only horizontal movement like this parallel to the surface over which the stream is flowing, if there is only laminar flow, there is no chance of eroding materials. Why? Because there is no component through which you can lift the material into the water and flow along with the horizontal one. But in the other hand, when we are dealing with a turbulent flow, in that case what is happening, you have a horizontal one as well as you have a vertical component. And always remember these two components are always, you can say, directly proportional. So if your horizontal component is increasing, your vertical component will also increase. So if you are having a turbulent flow like this, then you always have this vertical component which is influencing the particles to rise above the surface, and then the horizontal component is there to move the materials along its flow. So you can see this mixing of materials or particles above the surface is actually getting controlled by the presence of this vertical component within a turbulent flow, and the rest, the transportation, is done by the horizontal component. So now if I again look at this graph that we discussed a little bit when we discussed about sedimentology or sedimentary rocks, there again coming back to this graph, on one side I have the water velocity, on the other side I have the water turbulence. So you can see now I am grouping this into two halves. For one is the horizontal component, that is on the left side of the graph, and the other one is your vertical component that reflects the turbulence within in the stream or within the river. So that is plotted as the vertical component, and the magnitude of these arrows or the length of the arrow represents the magnitude. That means a larger arrow means higher velocity of water, smaller arrow means the low velocity of water. Similarly, like I said, it is directly proportional. If the water velocity is high, the turbulence will also be high. In the other hand, if the water velocity is pretty less, in that case the turbulence in the water will be also less. So now again on the bottom side you have these 5 types of particles based on grain size, like we discussed in our discussion on sedimentary rocks, that you have clay. For example, I am taking this 5 for our understanding purpose: clay, silt, sand, granule and pebble. So if I start with the last one, pebble, here, then I can say obviously pebble means they are of larger size. Obviously the weight will be little more in comparison to your granule, sand, silt or clay. So under the action of gravity, obviously there is a gravitational pull on this pebble, and that is why the pebble does not want to move from its own position. So now to move this pebble from its original position, what you need to first overcome the gravity exerted on the pebble under the earth's gravitational force. So your pebble to simply overcome that gravitational pull, you need a lot of turbulence to simply uplift the pebble into the surface. Then the rest of the work will be done by the horizontal component. But initially you need a higher turbulence to reach to this level where it overcomes the earth's gravitational pull. Then apart from that, when you lift it, it is not getting transported. Then after that, if you lift it a little more, then only it will be able to carry the rest of the pebbles within the stream. So what we see here, that the water turbulence that is affecting this or that is controlling this upliftment of the pebble grains will reach at a certain level, but this is just to, you can say, overcome the gravity exerted on the pebble particle. Then just after that you need a little bit more energy to transport it. So that is why a different curve is also positioned here. If I go back to the first one, you can see that the deposit is here. So you are lifting the pebble here at this level, then to finally transport it, to erode it from its own position, you need also a little bit more energy than that. So then after reaching this level, when it is touching the curve of erosion, then the rest of the horizontal component will do its role. It will move the particle from one end to another end. Similarly, if I talk about granule, here again first you have to lift the granule up to a certain level like this, where you need relatively less turbulence in case or in comparison to your pebble, but still you need certain amount of turbulence in your stream. That is why you need this amount of turbulence will overcome the gravity exerted, means the force of gravity exerted on this granule. Then finally, but to erode it, you need to again increase the energy a little bit more. Then only the horizontal component that is already present in that turbulent stream will do the rest. So that is how you can relate each and every of this kind of particle, be it pebble, granule, sand, silt and clay, based on this diagram. But to discuss more now, if I compare this graph, then I can see that it is actually the sand which requires the less amount of, or I will say the least or the lowest water velocity to transport it from one place to other. Now, why it is so? Again, if I look back at clay, now clay requires only very little turbulence to lift it up, because it is extremely I'll say it is quite lighter in comparison to all the size particles, be it silt, your sand, granule or pebble. So, what is happening? You need only this much energy to lift the clay particles, but you need to actually cross this much of turbulence and you have to gain this much velocity to actually move this particle. Now, why it is so? The reason behind that, and people didn't knew this earlier, because if I simply ask someone who don't have an understanding of this kind of result that we got from Flume experiment, this chart has been derived from experiments under Flume experiment. Flume is nothing but a large cylindrical, you can say, cylindrical tube where your different particles of different grain size has been kept, and the water from one end, water is flowing from one end of the cylindrical pipe to the other end. So, in doing so, it will transport, always it transport the sand first, but it is not transporting the clay first or not even the pebble first. So, why it is so? So, with years of Flume experiment, what people finally achieved this idea that always there is actually a laminar flow that is going on at near the surface. So, very near to the surface where your turbulence is minimum, your water velocity is also minimum, in that part of your stream or any river where you will get the laminar flow. It could be only, for example, a few millimeters thick zone or only a 1 millimeter thick zone, but there has to be always a laminar flow that is sitting beneath the rest of the turbulent flow of a stream or a river. So, here again if I go back to this curve, here I can say, so clay can be uplifted very easily with very little turbulence once, but it can't be transported because the problem is that here there is only laminar flow. So, here you are not actually getting any kind of turbulence. So, that is why it it is getting lifted, but it is not getting transported, because again you need it some kind of more turbulence so that it can go to that level where your rest of the horizontal component will play its role. So, the actual flow or the actual erosion of clay particles will takes place when the water velocity and turbulence reaches this much level. So, now if I consider all this, then I will say that sand is getting picked up here with a little turbulence and also moved with relatively low water velocity and obviously low turbulence in the water. So, if I can look at this diagram, then I can say that your sand is the easiest to pick up and your clay and pebble are the hardest to pick up. And again I will give you a simple example in case of a flood. For example, you left your home for some days and in between there was a flood, then when you will come back, you will see that you are getting muddy material all over your floor, your ground floor, there is all muddy layer. But if you simply remove that muddy part, or if you simply remove some of the mud from the upper part, then, or if you can look at the side of your building at the sectional view of that layer of sediments that have been deposited by the flood, you will see that the top part is dominated by clay obviously, but the lower part is still sand. So, that will also give you an idea. That means the sand got transported first to your home, then the rest of the mud or the clay particles that got transported and finally formed the muddy layer just sitting above the sand. So, this Flume experiment or the results of the Flume experiment actually put forward this idea of that how or why the sand particles are the most commonly transported materials through, be it your stream, be it your wind or any other agents of erosion. So, always sand will get transported first because it is easy to pick up as well as it is easy to transport with the minimum water turbulence as well as minimum water velocity just above the laminar flow. But it is always hard to pick up a pebble and then transport it. You require more energy. It is not very hard to pick up clay, but you need much more energy to transport clay. So that's why this graph very beautifully explains that why sand is the main, you can say, load that is getting carried by any river and stream. And in your again, if I think about the maturity of a river in its youth stage, you can think apart from sand, when the energy is quite high in terms of turbulence, if you are looking at a mountainous river or a river which is flowing down the slope of the Himalaya, obviously it will have much more turbulence in comparison to the same river when it is near the mouth. So when the turbulence is pretty high, then you can transport pebble along with obviously sand. You can transport pebble, but in the mature stage or the old stage of a river, like we get to see, for example, Ganga river near the Bay of Bengal, there the main load that is getting deposited on the Bay of Bengal, which is also referred to as the Great Bengal Fan, is mainly muddy material. So there the turbulence of the water is relatively actually less, but you can see that you have now picked up the clay along with the sand. You no longer have the ability to pick up the pebbles. So whatever material you are now depositing at the mouth will be rich in your particles like clay, silt and sand. The deposit of a river in the mountainous reaches of a river like that of Ganga near, for example, Gangotri, it will be able to transport even pebble along with sand. So sand is obviously present in any transport medium because it is easiest to pick up and flow, followed by obviously your these two end members. Clay is also hard to, it is easy to pick up, but it is hard to move the clay initially, but initially it is quite tough also to pick up pebble, but it is only possible when the river has very high amount of turbulence in it. So that's why you can now, just based on this graph, you can have a very clear idea that how this graph will help you to identify that what kind of deposits you will get, what kind of or which material will be eroded first, which material will be eroded at a later stage. So that was the first part of discussion on streams and rivers. We will go into the other or the second part of discussion on streams and rivers with further understanding about the erosional processes of rivers. Thank you.